In this video, we will discuss electric cars and how they function. We will primarily focus on the induction motors that power them and how these motors compare to the internal combustion engines found in most automobiles. Electric cars have an increasing prevalence in today's society. Some popular electric vehicles today include the Nissan Leaf, BMW i3, and perhaps the most famous, Teslas. These vehicles' recent increase in popularity is largely due to their smaller environmental footprint when compared to typical gasoline-powered vehicles, as well as their decreasing average prices. Here we have an image of the internals of a Tesla. A typical electric car consists of three major components: a battery, an inverter, and most importantly, an induction motor. The battery found in an electric vehicle is a lithium-ion battery. This produces direct current. The inverter then converts that direct current from the battery into alternating current. It also controls the frequency of this alternating current, which in turn controls the motor's speed. The induction motor then takes this alternating current and turns that into rotational motion. Now let's take a look at an induction motor. The alternating current induction motor was first invented by Serbian-American scientist Nikola Tesla in the late 1880s. Today, the induction motor is the most popular type of motor in the world. It consists of two primary components: the stator, the stationary portion, and the rotor, the rotating portion. Unlike a DC motor, which has its commutators and brushes rub against one another, the induction motor remains relatively quiet because of the lack of friction between the stator and the rotor. The stator is made up of thin steel laminations stacked on top of one another. Wire is coiled in three phases in slots of these laminations. This three-phase coiling strategy creates a rotating magnetic field when alternating current is passed through these wire coils. So what causes the stator to create a rotating magnetic field? The answer is due to the fact that there are three coils with changing currents. The alternating current supply causes the current through one coil to have a smaller current and therefore a smaller induced magnetic field. The current in this coil then rises and falls to the input of the AC frequency. Since the coils are out of phase and their current rises and falls at different times, the net magnetic field rotates. Faraday's law of induction states that if there are changing magnetic fields, there will be an induced electromotive force on a conducting loop. This force causes the loop to rotate, thanks to the right-hand rule. Instead of using a conducting loop, the rotor uses a series of conducting bars in a formation called a squirrel cage. The rotating magnetic field induces eddy currents in these conducting bars, which in turn create magnetic fields of their own. Due to Lenz's law, the conducting bars try to oppose the change of the magnetic field by rotating as well. The speed of an induction motor's rotating magnetic field is a result of the AC frequency. The rotor rotates almost as fast as the field, but cannot because of Faraday's law. If the rotor and field were to rotate at the same frequency, there would be no relative velocity between them, and therefore no induced current on the inducting bars. Instead, the rotor rotates slightly slower than the field. This difference is called slip. It is typically somewhere between 2 and 6%. This difference is why induction motors are considered asynchronous AC motors. The induction motor inside an electric vehicle can have a speed range between 0 and 18,000 rotations per minute. Due to this wide range of rotational speeds, electric cars utilize something called single-speed transmission or continuously variable transmission. Only one gear system is needed to convert the rotor's rotation to rotation in the car's axle. Internal combustion engines typically have a speed range of about 2,000 to 4,000 RPM. In turn, IC engine-powered automobile transmissions require a much wider range of gear ratios that need to be shifted between to produce different output speeds. Zooming out to look at the big picture, electric cars definitely have advantages and disadvantages. Some advantages include a low running cost. Electric vehicles go more miles per dollar than other cars. They make little noise, single-speed transmission, and most importantly, are more environmentally friendly than other cars. Some disadvantages are that electric cars tend to be more expensive, they take a long time to charge, and can't go far on a single charge. I hope this video helped you better understand how induction motors function, and more generally, electric cars. I hope you know more about their advantages and disadvantages when compared to internal combustion engine powered automobiles. Thank you.